Hey everyone, this is Andrew, back with the Organic Chemistry series. In today's video, we're going to be talking about the IUPAC nomenclature of cyclic compounds. Okay, so before we get started, let's refresh ourselves and remember the alkane prefixes, meth, eth, prop, but, etc. So when we apply this to cyclic compounds, specifically cycloalkanes, we can see cyclopropane would be a cyclic compound with three carbon atoms on a cyclopropane molecule. Same thing, if we move over to cyclobutane, it's simply four carbon atoms bonded in a ring structure. Same thing for cyclopentane and cyclohexane. Alright, so when we move forward with cyclic compounds, we must understand stability. Stability in organic chemistry is extremely important. In order to understand reactions and mechanisms, a great understanding of stability, you must have a great understanding of stability. So if we look at these molecules, a cyclopropane molecule has a heat of combustion per CH2 unit of 697 kilojoules per mole, as compared to the 653 kilojoules per mole for heat of combustion per CH2 unit in a cyclohexane molecule. This whopping difference plays a huge role in the molecule's ability to open up and react with other molecules. This all has to do with angle strain, steric strain, torsional strain. Angle strain refers to sp3 hybridized carbon atoms that differ from their 109.5 degree. So when we look at the ring strain for these molecules, we see that the cyclopropane molecule has 115 kilojoules per mole as compared to 0 for cyclohexane. So to go a little further with this and understand the bond angles and the angle strain that is actually occurring at the atomic level, we have to understand that. So, for example, in this cyclopropane diagram I have here, the ideal bond angle is a 109.5 degrees. So we see that this bond right here between these two carbon atoms is completely cut off from that 109.5 degrees. This is actually 60 degrees. According to Adolf von Baeyer and his Baeyer theory, 109.5 minus 60 degrees, for example, you can do this with any molecule, equals 49.5 degrees. You're asking yourselves, what does this number mean? So this molecule of cyclopropane differs from the ideal bond angle by 49.5 degrees. That is a tremendous amount of angle strain. So this leads to a lower stability. So how does this lower stability play out? In a reaction, for example, a cyclopropane molecule will open up its ring and react much more often than a cyclohexane molecule will, for example. First things first, going back to the rules for alkanes as well as alkenes, we know that what you want to do first is find the longest chain. Obviously, with a cyclic molecule, you can skip that part. So the first thing you want to do is find the first substituent. So we see here that this methyl group is on the first carbon. It's the first carbon because there are no other substituents. So this is quite easy. It's simply methyl cyclohexane. Alright, so with the next example, this one has more than one substituent. So in this case, in naming a cyclic molecule with more than one substituent, you need to make sure to make every single locant get the lowest number possible. It does not matter which substituent it is necessarily, unless you're dealing with an alcohol or any other higher order substituents. So with this molecule, we see that we have two substituents, 2 carbons away from each other. So we got next to each other, I shall say. 1, 2, 3, 4. This is an ethyl group. Here we have an isopropyl group. And then we have the methyl group as well. So the name of this compound would be, remembering the alphabetical rules, 1 ethyl, 2 isopropyl, 4 methyl cyclohexane. All right, so with this next one, going back to the alkene rules, we know that alkenes get priority. So even in this cyclic molecule, even with the chlorine atom, we have to give the substituents the lowest order possible. Now, if we did it this way, the chlorine would be on the 5th atom, on the 5th carbon atom. So we can't have that. We gotta go this way. 1, 2, 3, 4. Give it the 4th locant. So this molecule will be named 4-chloro cyclohexene. Okay, so with this next example, as I was talking about previously, there are higher order substituents that come first. There are no double bonds in this one. There are no triple bonds. But there is that. There's an alcohol. So when we number this one, the alcohol gets priority. It gets number 1, 2, 3, 4, 5. So this is a pentane, cyclopentane. And so when we name this one, it's simply two ethyl cyclopentanol. All right, we're on to the last example now. This one's a little bit different than the last ones. What we see here is we have a longer alkyl group, and it looks like it has a substituent. So how do we do this? How do we jump into this? If you know, go ahead, you can pause the video and do it, and then check back in. So when naming this, we see clearly we have a cyclohexane molecule. However, with this substituent, alkyl substituent, we have a 1, 2, 3. So this is a propyl alkyl group. And we see it has a substituent on it. What is this substituent? It's a methyl group. So when it comes to naming this, it's a little different than before. This name is 2-methyl propyl, because it's on the propyl alkyl substituent. 2-methyl propyl cyclohexane. Thank you for watching. If this was helpful, make sure to like it and subscribe. And leave comments if you have any other topics or subjects that you would like us to touch base on. We're going to continue with the organic chemistry for now, but we're also going to delve into biology very soon. And thank you for watching. See you in the next one.